Math 1314, Tyler Junior College, Section 2.5, Transformations of Functions. In this series of videos, we're going to do a couple of things. The first thing we're going to do is identify the graphs of some common functions. And I've got 7 or 8 of them in mind, depending upon how I feel. And on the board, we've got a column set up for the first 3. But after we've introduced ourselves and familiarized ourselves with these basic functions and their graphs, these common functions and their graphs, then we're going to talk about how we can change the functions by adding, subtracting, or multiplying values, or maybe inserting a negative here or there, and what impact that has on the graphs of the function. This way, when we're graphing some functions, we can do less work by taking advantage of more knowledge up front. So we're going to start with 3 functions. All of the functions that I'm going to show you have names in addition to their functions, but we're also going to look at their graphs, and from the graphs, domain, range, whether the function is increasing or decreasing, or where it is, and whether the function is odd or even based on its graph. Remember that odd and even functions have a certain symmetry. We'll discuss them as they arise. Our first function is called a constant function. A constant function is a function that says, give me any input, so we'll say f of x equals, but the output will always be a single number. Now, typically this single number is called c, but the value or the variable that you use to represent a constant is irrelevant. So all we're saying is that c is any real number. So it could be f of x equals 7, which means give me any input and the output will be 7. Or it could even be something as weird as f of x equals negative square root of 2 over 2. As long as the output is a constant and is independent of the input, it's a constant function. Now what would the graph of this look like? Well, if you think about it, and remember that f of x is just another way of saying y, this is y equals a constant, and the graph of y equals a constant is a horizontal line. So we would just have to locate c on the y-axis, wherever it would be. It could be positive, it could be negative, it could even be 0. And then it would be a horizontal line. The domain of this is negative infinity to infinity, because visually the graph goes forever to the left and forever to the right. However, the range is a single value. Now we could write it as an interval by saying bracket c, comma c, close bracket, meaning it begins with and includes c, but at the same time it ends with and includes c. But typically when your range is a single value or a finite number of values, you can just write it using set notation by putting in braces. Here are all the possible outputs. You know, like when we first did domain and range. As far as increasing or decreasing, this one is neither, because this graph is constant, and it's constant on its entire domain. And remember, all that means is that if you pick any 2 x values, the outputs are equal. In this case, they're always c. Is it an odd or an even function? Well, recall that an odd function will have origin symmetry, meaning if we take this whole picture and rotate it 180 degrees, the graph lands on top of itself. In this particular instance, it wouldn't, because if I turn this picture upside down, it would land down here. However, a function is an even function if its graph has y-axis symmetry, meaning the left half is a mirror image of the right half across the y-axis. In this case, it does have y-axis symmetry. So, this is an even function, but it's not an odd function except in one special case. If the constant were 0, then the graph would be on the x-axis, and if we turned it upside down, it would land on top of itself. So there is a rare exception where this is even and odd, and it's odd if, and only if, this is the only time it's odd, the constant is equal to 0. It's the only function that I know of that can be simultaneously even and odd. In other words, the only function whose graph can simultaneously have y-axis symmetry and origin symmetry. Any other such graph that has both would fail the vertical line test and therefore not be a function. All right, let's talk about the identity function. Now, why this is called the identity function is, it's not really beyond the scope of this course, but it's not at a point where we can correctly say why it's the identity function. The identity function is f of x equals x. In other words, the output is the input. The function says, give me a number and I'll give it right back to you. Some people say it's called the identity function because it preserves the identity of the input. If you put in 5, you get out 5. The true reason it's called the identity function has to do with function composition, but since we haven't discussed composition yet, I won't go any further. For those of you going down further math, more advanced math classes, if you take a course called Abstract Algebra, you'll learn about what's called groups and group theory, and in the context of group theory, it will be clearer why this is called the identity function. But for our purposes, let's just say it's called the identity function because it preserves the identity of the input. What would the graph look like? Well, the input equals the output. So if I put in 1, I get out 1. If I put in 2, I get out 2. If I put in 3, I get out 3. Or you can think of this as in slope-intercept form. Its slope is 1, its y-intercept is 0. But no matter how you view it, you get what I call a perfect diagonal line. And what I mean by a perfect diagonal line is that it makes a 45-degree angle with the x-axis, or more geometrically speaking, this line bisects the first quadrant, 45 degrees above, 45 degrees below. Of course, we could change the slope and change the direction of the line, change the tilt, change the steepness, if you will. But as a basic function, it's just that perfect diagonal line that bisects not only the first quadrant, but the third quadrant. The domain is negative infinity to infinity, because this graph goes forever to the left and forever to the right. For the range, you ask yourself how low and how high. Well, just like the domain, it goes forever down and forever up. So the range is also all real numbers, negative infinity to infinity. This graph is increasing, and it's increasing on its entire domain. The reason I'm specifying that is that we will have some graphs that are increasing on one half and decreasing on the other. So this is for emphasis that it's increasing on the entire graph. Is it an even function? Well, if you fold the right half over, it doesn't land on the left half. Is it an odd function? Yes. If I rotate it 180 degrees, it lands on top of itself. So it is an odd function. And the third one we're going to look at in this video is the absolute value function, which name describes it perfectly. It's f of x equals the absolute value of x. Let's see if the screen marker's working. No, it's too weak. We'll just use the red marker again. So it shouldn't surprise you that I'm about to write f of x equals the absolute value of x. But what does its graph look like? Well, think about it. If x is positive, then it's the same as this function. It doesn't change the input. Absolute value of these positive numbers alone. So for positive x's, it looks like this graph. But what would happen if we put a negative x in there? It would change the number's sign. So for example, if I went back 1, it would turn into a positive 1. Or if I went back 2, it would turn into a positive 2. And it wouldn't take you too long to figure out that the left half of the graph is the perfect diagonal line, but with a slope of -1, the diagonal line that bisects quadrant 2. Another way of thinking about it is to take the absolute value of this graph, all the negative y values have to become positive. The negative y values are on the left side over here, so to make them positive, you would have to reflect it up there. But either way you slice it, the graph of absolute value is a V. Let's see, what's the domain? Well, just like the others, it goes forever left and right, so negative infinity to infinity. But the range is not the same thing. Range is all the possible outputs or all the possible y values. This graph does not go down forever. The lowest point on this graph is at the origin, and the y value there, y coordinate there is 0. So this range starts at 0 and includes the 0, so bracket, comma, goes up forever to infinity. Here's the first example of a graph that is not doing the same thing in terms of increasing and decreasing on its entire domain. This graph starts out decreasing on the left. So it's decreasing on the interval that starts at negative infinity and it ceases to decrease once it hits 0. Then it starts increasing after that. So it's increasing on 0 to infinity. Remember, when we describe increasing and decreasing, we always use open intervals with parentheses. We can't include the 0 because how can we decide if at that point in time it's increasing or decreasing? The thing we decided on was it's kind of in transition, so it's neither. Is this an odd or an even function? Well, it does have y-axis symmetry, so it's an even function. In order to be an odd function, we would have to be able to rotate it 180 degrees and have it land on itself. But if we rotated it 180 degrees, it would be an upside down V and it wouldn't land in its original place. So these are the first three common functions I want you to be familiar with. A constant function, which is just a horizontal line. The identity function, which is this perfect diagonal line. And the absolute value function, which is a V. Or take the negative half of this perfect diagonal line and reflect it on the other side of the x-axis.